2, we'll start with what is something that you noticed or wondered from these sets of equations? Not all of the equations have parentheses. The ones that don't have parentheses, what do we call those? Okay, good. So then you could have also rephrased that by saying the first two in each set are in standard form. Standard form is kind of like our simplest form. You can't multiply anything out. It's already been multiplied. So if you kind of want to associate the S, standard form is the simplest form, that might be a good strategy. Did we have any other notices or wonders at table 2? All problems have or would end up with an x squared. So these are all quadratic. All right, they're all quadratic equations. Any other ones in table 2? All right, table 3, give me another notice or wonder. Okay. All right, all of the equations have x's. Any others, table 3? Okay, so what kind of form is g of x? Is it a form that we've seen before? Okay, so we have seen the form of g of x before. Does anyone know what we call it? Christina? Factored form. Are there any others in factored form? The q of x. The q of x. The other two are not factored form because factored form is written where they're all as factors. In h of x and r of x, the -4 is not being multiplied by anything. The 4 is not being multiplied by anything, so those technically aren't factors. Although you could multiply these out, but not all of it is factored, so we don't call it factored form. Any other notices or wonders that anyone wants to share? Yes?
The last two are.
The last two have where it's an expression squared. That is true. Have we ever seen something like the last one in this unit? So yeah, this is our vertex form. I haven't formally taught it yet, but I will right now to you guys. That's what our last two lessons are about. These last two formats in each set are vertex form. Guess what we can clearly see in our vertex form? You can clearly see the vertex in vertex form, and we'll talk about what part of it would tell us our vertex. But yeah, that is vertex form. You also have it on your paper, like a little diagram. That is what these are formatted as, okay? So there's that. Any other notices or wonders that we really want to share? Okay, if you didn't know already, set 1, these were all equivalent to each other. Set 2, these were all equivalent to each other. So if I graph each of these, even though they're all different, I would get the same graph. So also, when you walked in today, you picked up your practice constructed response test. For example, number 2 on that practice test, we talked about how you'll have a question like that, where you are given the graph and you're asked to give the equation. You could give it in any of the 3 forms. So on my answer key, I have all 3 forms for the number 2 answer. Whatever form you can derive the equation the best is up to you. But my personal favorite is vertex form. I would use that on number 2 on my test. But Yeah, other notices or wonders that I heard today was that in set one, there's a 4 in each part. Not necessarily in set two, is there a common number in each part? Maybe the -1, but I think that clears up everything else. Any other things we can talk about? All right, so to go, or to prove also that these are equivalent, if I were to multiply this out, and I think I have room under number 1 for you to do that. So say that I expand h of x and raise this to the power of 2, so remember that exponent to tell you to multiply the base by itself. So I'd have x plus 2 times x plus 2, and then that -4 is still there. I can multiply that out with FOIL, double distributing, whatever you prefer. I'll double distribute right now. What's x times x? X squared. What's x times 2? And it's positive, so I'll put plus 2x. If I distribute this 2, what's 2 times x? And 2 times 2. And then I still had that -4 from the original given problem. And then when I write my final answer in simplest form, I would combine all the like terms. So does the x squared have a like term? Does the 2x? What's its like term? I combine them, I get. And then I have these single numbers over here. What is 4 plus -4? So that actually ends up canceling out. That's why our standard form was just x squared plus 4x. So your other formats, the factored and the vertex form, can be multiplied out to give you your standard form, which is the simplest. But of course, you could also tell them to put it into the graph and give you the same thing. We could also prove that P and R are the same, but I don't think we really need to. Just know that if I were to multiply this out, I do get my standard form. Today we're doing a convalescent, just so you know. So the +4 I got from multiplying the 2 by 2. Okay. So then it was +4 and then this -4, which ended up canceling out. Okay, good question. Any other questions? So today we're doing a combo lesson, 15 and 16, all about vertex form, and then tomorrow we have another lesson about vertex form. Those are gonna be the last lessons of unit 6. So by the end of the lesson, you need to be able to identify when something is in vertex form and relate the numbers to the graph. Be able to graph when it's in vertex form, showing your maximum or minimum in the y-intercept. And how to tell me what it is, the maximum or minimum, without graphing it first. So that is our goal today. I record every day, in case you didn't know that. I think I say that every day too. Puzzle piece is lesson 15 and 16. And friendly reminder, we do have a binder check this Friday. So even if you are absent, like I need you to still go back, go through the lessons, take some notes down. You can do that by watching the videos. The notes are also all posted. You can just copy them on your own paper, or you can come get the papers from the bin, whatever one you're missing. But to get full points on the binder check, you just need to have all these pages and have a decent amount of notes written on the pages. It's really hard when sometimes like students will come to tutoring or come to Saturday Academy and they'll say, I don't know what's going on. And then I ask to see like, okay, well, do you have any notes? And they show me their notes and they're all blank. Like, no wonder you didn't know what was going on. It doesn't really look like you're paying attention or cared enough to write anything down. I feel like that's like the bare minimum step of you wanting to learn is you taking down notes. Like, you don't have to be smart to take down notes. If you choose not to take notes, that's like a -20% of your grade. The highest grade you would get would be an 80% if you get 100% on everything else. So I just don't know why, but, you know, do it, please. Some of you would be passing if you just did your binder check. or resubmitting your own binder check. So that's not gonna be a surprise, I hope, to anyone, that it's this Friday. Also, I will, during the binder check, test that practice constructed response test, the one that you picked up today. That matches the real test. The only thing I changed were the numbers and the graphs. I will test you the same exact skills on your real test. Also, I've been asking you to submit your coloring activity in Schoology. So make sure you do that. If you redid it, finished it, want to do the extra credit coloring part, do that in Schoology and we'll get that taken care of. Or you could just show me on Friday and I'll jot it down during the binder check. But after Friday, if you try to turn it in, I will take off some points. Doesn't mean you should never turn it in, but that's the deadline this Friday. So yeah, I talked about this, I think, enough. Any questions? Okay, so please, for the love, care about your grade. Please. But moving on, we are gonna go to this activity, or this first, actually. So we just talked about how all of those equations in each set are equivalent, and we're really looking at the vertex form. So here's a graph that goes along with the equation for graph H, or equation H. I know it's on your paper, I'm just writing it so it's on the same screen. I'm gonna ask you to relate the numbers that are in the equation to the graph that you see. So like, where can I see this -1, this 3, this 4? Where can I see this 2, this -4? That's what you're gonna talk about in your groups and have an answer ready, I'd say in about 2 minutes. Where can I see these numbers on the graph? Where do I see the -4 on graph H? Okay, that just happens to be a coincidence that it also touches -4 on the x-axis. In vertex form, I actually can't see the zeros very clearly. What form can I see the x-intercepts really clearly? Not standard. Factored form. So if I go back to my original data set, it is also a x-intercept of -4, but that's because in the factored form, it looks like this. In the vertex form, the only thing I can see really clearly is what? The vertex, it's in the negative. So try again, table 5, where else can I see the -4? So at the bottom of my view, the turning point of my graph, my vertex, that y value is -4. That's where it relates to the graph, okay, at the vertex. So then table 6, where do we see the 2? Oh, well. On the x-axis, it's a -2 for our x value of our vertex. Now that is intentional, so if you look at your little diagram, the one that's given to you for our vertex form, notice that HK, they use those letters for the vertex, because x and y would be confusing, we already have an x and y in the equation. But it's x minus whatever h is. So if h is a -2, like ours is, when I plug it in, it's x minus a -2. What happens with that double negative? It becomes a positive. So that's why in the equation it looks positive, but the h is actually negative. So the h is always opposite of how it looks in the equation. The k is always the same as how it looks. But it'll tell us our vertex as long as we remember that fact. Okay, questions on that? So then table 1, where do we see the -1 on our graph R? Okay, using the x-axis. That will not be my -1. Does anyone know where we see the -1? So think about what we did yesterday too, and we were doing all those transformations to the standard form. One of those transformations was when we did something to the A in standard form. We also, hold on, let me fix this. Okay, so here's standard form. Yesterday we changed the A, B, and C of standard form. This A has the same meaning as this A that's in vertex form. So it'll have the same transformations. When A is a -1, what does that do to the graph? No, it doesn't move. Well, I think I know what you're talking about. Maybe it moves the vertex, but that's not what I'm looking for. Anyone? So maybe have your notes out from yesterday. That might be helpful to you. But we saw that anytime that the A was negative, it reflected the graph. That's why this one opens downward. This one, the A was positive, so it opened upward. So make that note somewhere. When we have a negative A or just a -x², maybe they don't write the 1. The graph opens down. So when we have a negative A or -x², the graph opens down like a frown. When it's negative things happen to you, goes down like a frown. When it's positive, it's up like a smile. There's other things that happens when we put the number for the A, but when A is a 1 or a -1, that doesn't change it. So when it's negative, it'll reflect it. Okay, so good, any questions? That's where we see the -1. The -1 reflects the graph. Flips it upside down. Where do we see the 3 and the 4? The vertex. My vertex is at 3, 4. And the H always is the opposite of how it looks in the equation. So here it looks negative. That's because I plugged in a +3 into x minus H. Yes. Yes. And then K always matches. So good, any questions? Good on that? All right, moving on. We're gonna do something similar to what we did yesterday, so you can see a table similar to what we did yesterday, but this time you're graphing your parent function, y = x². And you are doing these things listed. You have 2 on the front, 2 on the back. Let's review, let's understand what it's asking you to do before I just let you try it. This first one says adding different numbers to x before it is squared. So which of these letters, A, H, or K, is it asking you to change basically? If it wants you to add different numbers to x before it is squared. I heard something, but I'm not sure what I heard. Not the A, that would be multiplying x² by something. The H. So basically you can do x plus whatever number you want in parentheses squared. And you can also add negative numbers, so maybe put a negative example in there too. I'll let you pick the numbers, because that's what you're doing. For the next one, we're adding different constant terms to y equals, and it has an expression this time. This time it wants you to do Instead of the parent graph, compare it to x minus 1 squared. But it wants us to add different constants. So what's a constant?
The number of being very,
That would be a coefficient.
the number of being times one.
No. If I want to add a constant, a number by itself is what a constant is. So you could add any number you want. You can even add negative numbers and study rules like you're subtracting, but same thing, you can add a negative, compare. And make your observations over here. So then the multiplying this expression by different coefficients, that's where you're changing the A. So maybe if you wanna make a note of that over here, this changes the H. This changes the K. Down here, we're changing the A and seeing how that affects our parent graph or whatever they're trying to do. Okay, so do that, if you have 4 people in your group, a good suggestion would be each of you take a row, play around with the parameters and share your observations on it. If you have less than 4, then you'll have to be creative, but, do that. I'm gonna ask you for the observation in about 4 minutes. When we added different numbers to the x before it is squared, what did we notice in our change to the parent graph? Or can you tell me what you added or subtracted? What is it? 3, so like adding 3 and then maybe an example of when it subtracts 3. Now, what did that do to the graph? It shifts it in what direction? It switches what? Sorry, what? I cannot hear you. You need to speak up. Are you guys gonna go to job interviews and like whisper when they ask about you, tell them about yourself? I just need to be able to hear you. How did this change the graph? How did adding or subtracting a number change the graph? It switches sides? What does that mean? Does it go up, down, left, right? Does it get smaller? Does it get wider? Okay, so it shifts it left or right if we are changing the H. All right, you can memorize if you're plugging in a positive H or negative H. I personally don't like doing that. Oh, I put that on your desk so that you can clean it off. Thank you. Anyway, I don't memorize that because I know that H is always opposite of how it looks in the equation. So I just memorize how it looks in the equation. So if it's shifting left, that must be that it was x plus a number in the equation. And if it's shifting right, then it's x minus a number in the equation. That's how I would choose to memorize it instead of a positive H or a negative H. Okay? But yeah, and it shifts it however many units you put in. So for example, if it said x plus 3, then it shifted left 3. If you did minus 3 in your equation, then it went right 3. Or if you did plus 7, it went left 7. Minus 7, it went right 7. Okay, questions on that? It didn't go up or down, it didn't get smaller or wider, that's the only change that H does. Because H is the X of your vertex. So then table 2, what about when you add different constant terms to an expression? Give me an example of something you added. All right, and then let's also do one where we subtract a 2 or add a -2. What does that do to our graph? It shifts it up or down. That doesn't move it left or right at all. It doesn't make it skinnier, wider. For some reason, they wanted us to add it to this rather than the parent graph, so use that as like your parent graph and then compare it, like put it in a different cell with transformation and then compare how it changed. If it went up, that was because your K was positive. If it went down, that's because your K was negative. Good, any questions on that? You're gonna notice, and it moves up or down however many you put. So here it goes up 2, here it goes down 2. Table 3, what about when we multiply different coefficients by this expression? What's something you chose to multiply it by? Okay, so then that means they would have typed in something that looks like this. So we're changing the A each time. For some reason, they wanted you to add it to this expression. I suppose you could also do it to the parent graph and get the same effect. But when I times it by this, and let's do a negative example of that too. How does that change the graph? Okay, there's something wrong with how that was entered, so let's see.
Oh, yeah, exactly.
Okay. Right. No problem.
Oh.
Okay, so let's have our original so that we can better compare it. For some reason, they want this one to be our original. Okay, so in a different cell, I'm gonna put the transformed one. And we are timesing it by, for right now, a 3. Okay, so red's my original, blue is my transformed one. Did the graph move up, down, left, or right at all? What was the change? It got thinner, more narrow. How do we say that in our math vocabulary? It was vertically stretched. You could still write thinner so that you can identify it, so that you know what it means to be vertically stretched. But that's what we call it in math, if it gets more narrow. And then also pay attention to your original versus your transform. Don't look at this and be like, oh, it got wider. The red was our original, okay? Now, what about if I times it by -3? Let's see what happens. How would you describe that change from the original? It reflected, is that all it did? It reflects and it's still vertically stretched. So it reflects and vertically stretched. So the vertical stretch comes from multiplying it by a number greater than 1 or less than -1. The fact that it's reflecting comes from it being negative. That same thing where if it's negative, it goes down like a frown. So that's that change. All right, almost done. Table 4, what about multiplying it by a different coefficient between -1 and 1? What's something you could have multiplied it by? Say 5. 5 is not between -1. So pick another number. What did you say? Okay, 0.5. Let's try that. And let's do it by x squared. They didn't specify that we have to do it by the other anymore. So we'll type in 0.5x squared, and let's also see when it's negative, how that changes. But as long as it was between -1 and 1, and it was not 0, because we know multiplying it by 0 would just make the whole thing 0. We'll see how that changes it. Anyone want to make a prediction? Do you think it'll move it up, down, left, or right? What would it probably do? Good, vertical compression is how we actually call it, but yes, it's vertically compressed. Which does mean that it is getting wider. And then if I times it by a negative 0.5x squared, will it still be vertically compressed? What else will happen? Since it's negative, it'll reflect. Good. So vertical compression and reflection because of the negative. All right, so yeah, that's the gist. That's how A changes the equation. That's why you can still sometimes see it in your vertex form. All right, so there's that. It's wider, it's reflected. If I take away the negative, it's the same direction opening, but it's still wider. All right. Questions on that? Okay, so that is that activity. One more, and we'll call it a day. And this last one, you're encouraged to not use graphing technology. So you have a series of different equations right here. I'll go back to the other page, I'll pause it and I'll go back to it, but you are going to tell me what the vertex is without graphing it. Because from the equation, you should be able to identify that. You're also gonna tell me if it opens up or down, again, without graphing it. So do that, I'll give you 5 minutes or so. When and if you finish that early, do work on the practice, but this is what we're doing next. I'm gonna go back to this page, so that way anyone that was writing can still get those answers. But now you are making predictions without your graphing. Yes, Priscilla? Yes, and then Jaden B. So table 5, what is the vertex of this equation? What? And remember, the goal is to do these without graphing technology, so if you did it with graphing technology, you technically cheated. But because really you should be able to tell if it's in vertex form, what the vertex is within a few seconds. On your test, should you check with graphing technology? Yes, absolutely. But, yeah. HK in our vertex form. HK is our vertex. I will not be providing that to you on the test, just so you know. You would need to know that. And you would also need to remember that H always looks different in the equation than what it actually is. So it looks positive here, it's actually negative. K always matches, and since there was no plus a number or minus a number, it would have to be 0. Good, any questions on that? All right, table 6, does this one open up or down? Up. Because the A is positive, there's nothing written for the A. So it's a positive 1, it opens up. All right, table 1, so whoever was the reporter last, let's go 1 to the left. So table 1, what's my vertex of this one? 4, 8 is correct. Table 2, does this one open up or down? Good, that is correct. The H always looks opposite of how it looks in the equation. K always matches. Table 3, what's my vertex of this one? HK is my vertex. Here's my equation for reference. What's my vertex for this one? Pretty good. Table 4, does it open up or down? This one actually opens down. Because there's a negative right here, that means A is a -1, the graph will open down because A is negative. Okay? You won't see the negative in the parentheses, I'll tell you that, they usually pull it out and put it in the front. But yeah. Table 5, what's my vertex of this one? Close. 0, -7. So this time there's nothing in parentheses with the X, that means there's no H, or the H is 0, because we wouldn't write X minus 0, it's just X. There's that, K is -7. Table 6, does this open up or down? It opens up, because the X squared is positive, the A is positive. All right, rotate 1 to the left again. Table 1, what's my vertex of this one? Okay, good, that is correct. Table 2, does this open up or down? No. It opens up. That's a positive. The positive or negative part of it tells you if it opens up or down. What does the 1/2 tell us about it? Well, because it's positive, yes, it opens up, but what about that it's 1/2? It makes it wider. Okay, all right, anyway, where am I? Table 3, what's my vertex of this one? $50 is correct. Remember, H is always opposite of how it looks in the equation. So it should be negative on it, yes. And positive H. Table 4, does this one open up or down?
Yeah.
It opens down because of this negative that's out here. Table 5, this last one, still same concept. It's the vertex. And what did you say for a second one? Okay, good. Always opposite of how it looks, negative end. The K, this will always match the same sign. Table 6, does this one open up or down? It opens up. If it was negative, they would show that it was -8, so then it must be positive. All right, good. You still have a decent amount of time to do a few more problems on your practice. Lesson 5 or lesson 15/16, one type of piece for the 2 lessons. Don't lose your notes. If you finish things early, start getting your notes together for Friday. And your practice test, you can get that done.